Okay, so have you ever wondered how much energy is just locked away inside a chemical reaction? It's not some abstract idea, it's a real, measurable quantity. And today, we're going to learn how to basically read the energy of the universe, one reaction at a time. Let's dive in. It really all starts with a super simple question, right? Why does a campfire feel warm? Or, on the flip side, why does an instant cold pack feel so incredibly icy? The answer to both is all about the silent transfer of energy that's happening every single time chemical bonds are broken and new ones are formed. Now, to get a handle on this, scientists need a specific tool. We're not just guessing about the heat, we are measuring it. And the concept we use to do that is called enthalpy. That's our key to unlocking this whole flow of energy. So, what exactly is it? Formally, enthalpy, and we represent it with a capital H, is the total heat content of a system. That's everything, the internal energy of the molecules, plus the energy tied up in its pressure and volume. But, and this is the key, in the real world, we almost never look at the total enthalpy. What's way more useful is measuring the change in enthalpy during a reaction. Okay, so before we can measure any change, we have to be absolutely crystal clear about what we're measuring and where. We've got to define our reaction zone. In chemistry, we basically split the entire universe into two parts. You have the system, that's the thing we're actually studying, the chemical reaction happening in the beaker. Then you have the surroundings, which is, well, literally everything else. The glass of the beaker, the lab bench, the air in the room, even you standing there. That heat you feel from a campfire, that's just energy moving from the system, the burning wood, to the surroundings, which of course includes your hand. Now, we can actually control how the system and surroundings interact. An open system, like coffee in a mug, can exchange both heat and matter. Steam escapes and the coffee cools down. A closed system, say you put a tight lid on that mug, only exchanges heat. The water vapor is trapped, but it'll still get cold. And finally, an isolated system. Think of a perfect thermos. Exchanges nothing at all. Of course, in the real world, a truly perfectly isolated system is pretty much impossible to achieve. All right, we've set our boundaries. Now for the main event. How do we actually put a number on this energy transfer? How do we calculate it? This right here is the absolute key. The change in enthalpy, which we write as delta H, is what it's all about. You calculate it by taking the final heat content of the products, that's the stuff you end up with, and you subtract the heat content of the reactants, the stuff you started with. It's a simple subtraction, but it tells you exactly where the energy went. And when you do that math, you're only going to get one of two results. If your final number is negative, it means the system lost heat and gave it away to the surroundings. We call that an exothermic reaction. But if the number is positive, it means the system had to pull in or absorb heat from the surroundings, and that's what we call an endothermic reaction. Let's make this real with a classic example. An exothermic reaction is probably the kind you're most familiar with. Just think about lighting a gas stove or a barbecue. You are witnessing the combustion of methane. So here's what's happening. One molecule of methane is reacting with two molecules of oxygen, and what you get out is carbon dioxide and water. Now remember, every reaction is about breaking old bonds and making new ones. It takes some energy to break the bonds in methane and oxygen, sure, but a much larger amount of energy is released when those new, super stable bonds in CO2 and H2O are formed. So where does that extra leftover energy go? It's released as heat and light. The change in enthalpy here is negative 890.4 kilojoules per mole. Let's really break that number down, because every part tells a story. That minus sign? That's your big signal. It screams exothermic. Heat is leaving the system. The number, 890.4, tells you just how much energy. And per mole is just the standard way chemists count. It means for every batch of methane you burn, a huge 890.4 kilojoules of energy is released. That's why it feels hot. All right, let's look at the complete opposite scenario. An endothermic reaction feels cold for a very simple reason. It's literally sucking heat energy out of its surroundings to power itself. The classic example you've probably felt is one of those chemical cold packs you use for an injury. A really important industrial example of this is breaking down calcium carbonate, which is basically just limestone, into lime and carbon dioxide. This reaction is not going to happen on its own. You have to pump a ton of heat into it to get it to go. And the number tells the whole story. The value for delta H is positive 177.8 kilojoules per mole. That plus sign is our signal that this is endothermic. It tells us the system has to absorb 177.8 kilojoules of energy from the surroundings for every mole or every batch of limestone that decomposes. It's pulling heat in. Look, numbers and equations are powerful, but sometimes a picture is worth 1,000 kilojoules, right? So let's visualize this energy journey with something called an energy profile diagram. Okay, so every one of these diagrams has three main parts. The vertical axis, the y-axis, represents potential energy. You have a starting line, which is the energy of your reactants. You have a finish line for the energy of your products. And in between, there's this hump, this peak, called the activation energy. Just think of it like the initial push you need to get the reaction started, like the spark you need to light the methane. So, for an exothermic reaction like our burning methane, the energy journey is all downhill. See how the products finish at a lower energy level than where the reactant started? That drop, that difference in energy, is the exact amount of heat that gets released into the surroundings. And that's exactly why delta H is negative. And you can probably guess the opposite is true for an endothermic reaction. The journey is an uphill climb. The products end up at a much higher energy level than the reactants. The reaction had to absorb all that energy from the surroundings just to make that climb, and that's why delta H for these reactions is positive. So, we've defined our terms, we've looked at the math, we've even visualized the process. But what's the big picture here? Why does any of this actually matter? It really just boils down to these four key things. 1, enthalpy change, delta H, is how we precisely measure the heat flow in a reaction. 2, a negative delta H means it's exothermic, it gives off heat. 3, a positive delta H means it's endothermic, it takes in heat. And 4, we can draw a map of this entire energy journey using those profile diagrams. And look, understanding this stuff isn't just for a test. It is fundamental to, well, almost everything. From developing more efficient rocket fuels to creating new smart materials or even designing self-heating coffee cans or self-cooling medical supplies. So I'll just leave you with this thought. Now that you can read the energy hidden inside a Hey, welcome to The Explainer. You ever wonder how the calories on a food label are actually figured out? Or how chemists can compare the energy you get from different fuels, like apples to apples? Well, it all comes down to having a standardized way of measuring chemical energy. Today, we're going to break down the science of standard enthalpy. So let's dive right in. And that's a really great question, right? I mean, if one reaction happens in a freezing cold lab and another happens on a hot day, the results are going to be different. So how on earth are you supposed to compare them fairly? To do that, scientists needed a universal baseline, a common starting point for everyone. And that's where something called standard conditions comes in. Think of this as the official rulebook. It levels the playing field, making sure that when we measure the energy change of any reaction, anywhere in the world, we're all speaking the same language. Now, under these conditions, every single substance has what we call a standard state. It's basically just the default, most stable version of that substance. For oxygen, it's a gas. For carbon, it's solid graphite, not diamond. This is our ground zero for everything that follows. So what are these rules exactly? Well, as you can see here, we're talking about a specific set of values. A temperature of 25 degrees Celsius, which is 298 Kelvin, pretty much a comfortable room temperature. A pressure of 1 atmosphere, just normal atmospheric pressure at sea level. And if you're working with solutions, a concentration of 1 mole per cubic decimeter. By locking in these three values, we make sure any energy changes we see are because of the chemistry itself, not because the room was hot or the pressure was weird. All right, so now that we've got the rules of the game set, we can start exploring the different kinds of energy changes, or enthalpies, and each one describes a very, very specific type of chemical event. Okay, first up, we've got the enthalpy of formation. This is all about building something. Specifically, it's the energy change that happens when you create exactly 1 mole of a compound from its raw, basic elements in their standard states. You can think of it like the energy cost or profit of constructing one single type of molecule. So let's look at methane here. Making 1 mole of it releases 74.8 kilojoules of energy. Now, that negative sign, that is super important. It tells us energy is being released, that the reaction is exothermic. It's like a ball rolling to the bottom of a hill. The final product, methane, has less energy and is therefore more stable than the ingredients you started with. This is also why we say elements in their standard state have a formation enthalpy of 0. They're our baseline, right? You can't form something that already exists, so the energy cost is 0. All right, next up is one you're probably pretty familiar with, even if you don't know the name: enthalpy of combustion. This is the heat that's given off when you burn 1 mole of something completely in oxygen. This is the science behind everything from gasoline in your car to the calories in that sandwich you ate for lunch. And here's the thing about combustion: it is always exothermic. No exceptions. It always gives off energy into the surroundings. I mean, that's fundamentally why fire feels hot, right? It's literally releasing energy. Then there's the enthalpy of neutralization. This one gets really specific. It's the heat given off when an acid and a base react to create exactly 1 mole of plain old water. And what's so cool about this is the number you get. For any strong acid reacting with any strong base, the value is almost always right around -57 kilojoules per mole. But why is it so consistent? Well, think about it. With a strong acid and a strong base, they both completely break apart into ions in the water. So what you're really watching is just one thing happening over and over. A hydrogen ion meets a hydroxide ion, and they make a water molecule. The other ions are just spectators. And last but not least, let's talk about the enthalpy of solution. This is just the energy change when you dissolve something. This one's really interesting because it's a bit of a two-way street. Sometimes, like with calcium chloride, dissolving it is exothermic. It releases heat and makes the water feel warm. But other times, with something like ammonium chloride, it's endothermic. It actually sucks in heat from the water, making the solution feel cold. It's all about a battle of energies. It takes energy to break apart the solid, but you get energy back when it bonds with the water. Whichever one wins determines if it gets hot or cold. Okay, so all these definitions are great, but where do the numbers actually come from? For that, we have to head into the lab and actually measure the stuff. So, a really classic way to do this is to burn a known amount of fuel right underneath a container of water. The logic is pretty simple. The heat that the burning fuel gives off gets absorbed by the water. So if we measure how much the water's temperature goes up, we can calculate how much energy was released by the fuel. Yeah, but as anyone who's done this in a high school lab knows, it's never quite that perfect. You're always going to lose some heat to the air. The fuel might not burn completely, leaving behind some soot. And some of the water might evaporate, and that carries energy away with it. These little errors are why the number you get in a simple experiment is usually a bit different from the official value in a textbook. Okay, so let's say we've done our experiment as best we can. How do we take that temperature change we measured and turn it into an actual hard number for energy? For that, we need the master formula. And this is the magic formula. Q equals mc delta T. It's so simple, but it's incredibly powerful. This equation is the bridge that takes us from something we can see and measure, a change on a thermometer, to the thing we really want to know: how much heat energy was transferred. So let's really break this down piece by piece. Q is the heat energy we're looking for, measured in joules. M is the mass of the water we heated up, in grams. Delta T, that little triangle just means change in, is just the final temperature minus the initial temperature. And C, well, C is the special number that ties it all together. Now that letter C is really important. It's called the specific heat capacity. For water, it's a specific number, 4.18. And what that means is that it takes exactly 4.18 joules of energy to make the temperature of 1 gram of water go up by 1 degree Celsius. It's just a fundamental property of water itself. All right, let's put this into practice. Imagine we're in the lab right now. First, we measure the mass of our water. Let's say it's 100 grams. Then we measure the temperature change. Let's say it started at 20 degrees and ended at 30, so our delta T is 10 degrees Celsius. Now we just plug it all in. Q is going to be 100 grams times that constant for water, 4.18, times that 10-degree change. You multiply it all out, and you get 4,180 joules. See? It's a direct, step-by-step path from your measurements to the final answer. And that really brings us to our final big question, doesn't it? We just saw that a simple lab experiment is always going to have some errors. So how do we get those super precise, down-to-the-decimal point numbers you see in data tables? The answer is that scientists use much more sophisticated equipment, called bomb calorimeters, that minimize heat loss. And they use careful techniques and mathematical corrections to account for the tiny errors that still exist. It's really the difference between a good classroom estimate and a true scientific standard.
Have you ever wondered how scientists measure things they can't, actually measure? I mean, think about it. Some chemical reactions are over in a flash, some take literally millions of years, and others are just plain impossible to do in a lab. So how in the world do chemists figure out the energy involved? That's what we're diving into today. This right here is our central puzzle. How do you measure the energy from a firecracker's bang, which is over in an instant? Or what about the almost impossibly slow energy change as a diamond turns into graphite over geologic time? You just can't. But chemists have come up with some incredibly clever workarounds, using pure logic to calculate what they can't directly see. Let's find out how they pull it off. So, we're going to build ourselves a toolkit today with 3 really powerful methods. First, we'll get into Hess's law, which is kind of the master key that lets us find our answer indirectly. Then, we'll look at a super detailed application of that, a sort of energy map called the Born-Haber cycle. After that, we're going to zoom all the way in to the atomic level, calculating energy by literally counting up the bonds that break and form. And to wrap it up, we'll talk about how to know which tool is the right one for the job.
All right, first up is the absolute cornerstone of this whole idea, Hess's law. The best way to think about it is like climbing a mountain. It doesn't matter if you take the super steep, direct path or the long, scenic, winding trail, your change in altitude from the bottom to the top is exactly the same, right? Well, it turns out chemical energy works the exact same way.
The fancy science term for this energy change is enthalpy, which we call delta H. And the reason Hess's law works is because enthalpy is what's known as a state function. Now that sounds complicated, but all it really means is that the universe doesn't care how you get from point A to point B. It only cares about the energy difference between your starting point and your ending point. The path you took is totally irrelevant, and that's the loophole that we can cleverly exploit.
This is so cool. It basically lets us treat chemical reactions like they're just simple algebra problems. If we know it takes a certain amount of energy to go from A to B, then the reverse trip from B back to A uses the exact opposite amount. You just flip the sign. If you double your recipe, you double the energy change. You just multiply. So if we can find a few different reactions that we can measure, and we can arrange them so they add up to our impossible reaction, we just add up their energies to get our answer. It's such an elegant solution.
Okay, so if Hess's law is the general rule, let's check out a really powerful and specific way it's used. Our next tool, the Born-Haber cycle, is basically Hess's law on steroids, and it's built to solve one very specific, very tough problem.
And that problem is finding something called lattice energy. This is the huge burst of energy that gets released when a bunch of scattered, gassy ions suddenly snap together and lock into a perfect crystal structure, like when table salt forms. You can't just whip up a cloud of sodium and chlorine gas ions in the lab and measure this energy release. It's impossible. So, we have to build an indirect path to the answer.
The Born-Haber cycle is that path. This is a really clever loop. We start with the raw elements, and we measure the total energy it takes to turn them into the final crystal. That's our known direct route. Then, we map out this long, roundabout way, going through all these individual steps, turning a solid into a gas, ripping off electrons, and so on. We can measure the energy for every single one of those little steps. The only piece of the entire puzzle we don't know is that final huge release of lattice energy. But since both paths start and end at the same place, their total energy change must be the same. It just becomes a simple algebra problem where we solve for the one missing number.
Now for our third tool, this one takes a completely different approach. Instead of messing with entire reaction equations, we're going to zoom way, way in and look at the energy of every single chemical bond that's being broken and every single bond that's being formed. It's a real bottom-up approach.
You know, the core principle here is actually pretty simple. Every chemical reaction is just a trade-off. First, you have to put energy in to break the old bonds apart. Think of this as your upfront cost. It's an endothermic process. Then you get an energy payoff when new, stronger bonds form, which releases energy out. That's an exothermic process. So the total energy change for the whole reaction is just the difference between your cost and your payoff.
Let's make this real with one of the most famous reactions out there, making water from hydrogen and oxygen gas. We're going to calculate its total energy change, step by step, just using average bond energies.
First things first, the upfront cost. Before we can even think about making water, we've got to break apart the molecules we started with. That means we have to snap all the HH bonds in the hydrogen and all the O equals O double bonds in the oxygen. The total energy we have to pump in to get that done is 685 kilojoules for every mole. That positive sign tells you this is our investment.
And now, the good part, the energy payoff. Once those individual atoms are floating around, they rearrange to form water. And in doing so, they form 2 moles of very, very stable oxygen-hydrogen bonds. The creation of these new bonds releases a massive 928 kilojoules of energy. And that negative sign is crucial. It shows that energy is flowing out of the system.
This all leads us to our main formula. The total enthalpy change, our delta H, is simply the sum of all the energy of the bonds we broke minus the sum of all the energy from the bonds we formed. It's your energy cost minus your energy payoff.
Okay, let's just do the math. We put in 685 kilojoules to break the bonds. We got back 928 kilojoules when the new stable water bonds formed. So 685 minus 928, that gives us a net change of negative 243 kilojoules per mole.
And this is just a perfect illustration of what that negative number really means. The reaction is exothermic. It gives off heat. Why? Because the energy payoff we got from forming those super strong OH bonds was bigger than what it cost us to break the original bonds. The final result is a net release of energy. It's that simple.
So we've just walked through 3 totally different methods, but they were all designed to solve that same initial problem: how to calculate the energy of reactions we just can't measure directly. Let's put them all side by side so you can see when you might use each one. And there you have it, your complete toolkit. Hess's Law is your go-to, your general strategy for when you can piece together an answer from other known reactions. The Born-Haber cycle? That's your specialized piece of equipment that you bring out for one very specific job: finding lattice energy. And using bond energy is your ground-up approach, building the answer by looking at the cost and payoff of every single bond, which gives you a really solid estimate.
When you get right down to it, all of these amazing methods work because of one fundamental property of our universe: energy is a state function. The path doesn't matter, only the start and the end. It really makes you wonder, doesn't it? What other invisible forces out there, what other things in our world work this way? When does that messy, complicated journey in the middle not actually matter as much as just knowing the difference between the beginning and the end? It's a pretty powerful idea, all born from the need to measure the impossible.